In this video, we'll be discussing gas chromatography. We'll start by going through different columns, the stationary phase, and a critical part of the instrument. Then we'll go into some nuts and bolts, talking about the injectors, the inlet, and in there we'll cover split ratios, then the carrier gas, as well as column oven temperature programming, and we'll finish up with detectors and looking at some of the example data produced by those detectors. Here is one of our GC instruments. Let's take a closer look at some of the components. So we have the detector, the auto sampler, the inlet, and then the column in the column oven. So you can see the auto sampler a little bit better. You can always make manual injections, but auto samplers sure are nice. So let's open up this front here and look inside so we can see the oven. You can see the column inside the oven, and it's connected to both the inlet and the detector. So your sample is injected into the inlet, and the inlet heats the sample into a gas and pushes it onto the column. It travels through the column, and then as things elute from the column, they travel into the detector where they are detected. You can see that fan in the back. That helps to regulate the temperature. So the oven can move relatively quickly. It can heat up relatively quickly, and it can cool down relatively quickly by opening up the back and blowing that fan to blow the hot air out. And that can really save us a lot of time when we're running gradients and things, temperature gradients. So we'll look at the GCMS also. This has a GC on one side over here, and the detector here. So if we open up the oven, you can see there is, the column is connected to the inlet on the top. It comes in from the inlet, and then on the side, it is connected to the detector. The detector in this case is a lot more complicated. On the previous instrument was a little FID, flame ionization detector. In this instrument, it is a whole mass spectrometer. So the capillary column runs into the mass spectrometer. Here you can see an example of a capillary column sold by a company called ResTech. They make excellent columns. Okay, capillary columns are quite different than what we saw in liquid chromatography. They're going to be very, very narrow, and they're going to be made from fused silica with a coating in them. Now, fused silica is essentially fancy glass. We talked last time about how anything we can, we'd use silica for, because silica is cheap and ubiquitous, relatively speaking. If you coat it with that brown polyamide polymer that you see on the outside there, you can curl it. And that lets us logistically make these really skinny, narrow columns that we just coil on top and on top and on top of each other. This is actually a 30-meter column. That is a very long distance. So people are between, typically 1.5 to 2 meters tall. A very tall person will be 2 meters tall. So you can imagine having 15 or 20 people stacked head to toe. That's how long this column would be if you unwound it. So here's what it actually looks like. You can see the brown coating on the outside. That's protective, and that lets you bend the column around itself. But within that, you have this fused silica, which, like I said, is essentially fancy glass. Now, the fused silica is going to have an exterior wall, and then within that is the inner diameter of the column. This is where everything is actually happening. This is what the gas travels through. We're going to take this a step further, and we're actually going to coat the inner diameter of that fused silica column with a stationary phase. We're going to coat it with a stationary phase, and that stationary phase is going to be what the analyte traveling through the column actually interacts with. So here we have an electron microscopy image looking down the barrel of that column, so you can get a good sense for what some typical dimensions are. You can see that polyamide sheath on the outside, and then the inner circle there is the fused silica, the fancy glass. And it's typically about 250 microns or 250 micrometers in inner diameter. That's a very, very common column size. But you can't really see down. You can't see through this hole with your bare eyes. It's a very, very small hole, and it has to be small. It has to be small to be functional as a reasonable chromatography column. That's a tiny inner diameter. So you can see here this inner diameter, this is what we're talking about. And this one is, in fact, 250 micrometers. And then inside a very, very narrow film of polymer coating is going to function as a stationary phase, and it's going to be a really thin coating inside this silica tubing. It's going to tend to be, the diameter of that coating is going to tend to be 1,000 times smaller than the inner diameter of the column. So 250 nanometers is a pretty common thickness for a stationary phase coating. So here's a table of some pretty common columns, some pretty common capillary columns that you'll see in GC. And you see here that this is from Sigma Aldrich. It's a pretty ubiquitous supplier of chromatography equipment. You can see that their columns that they sell range from 0.1 millimeters or 100 micrometers up to 0.53 or 530 micrometers. And 0.53 is actually a pretty big column. A really common column, probably the column you're going to see most often in forensics, is going to be the 0.25 millimeter inner diameter column. That's 250 micron. The stationary phase thickness for most things is going to be 250 nanometers or 0.25 micrometers. An exception to this is going to be for blood alcohol, for tiny volatiles. In that case, you have to have a pretty thick film to get those guys retained because they like to boil off. And a really common length is going to be 30 meters. So a very, very common column in forensics is going to be a 250 micron inner diameter column with a 250 nanometer film on the inside there, 30 meters long. Of course, there are going to be exceptions to that. Some people who run explosives like to run shorter columns. We'll talk about thermal degradation later. But explosives tend to undergo thermal degradation, and they want to get the runs done. They want to have those compounds in the hot oven as little time as possible. So a lot of times they'll cut down on the length of the column and run a pretty short column. Short being 5 or 10 meters, which is still giant compared to an HPLC column. But 30 meters is a pretty typical length. In the petrochemical industry, sometimes they'll go out to 50 meters or 100 meters for these GC columns, but 30 meters is pretty common in forensic science. So we've got to coat the inside of that capillary with a stationary phase. This is a really common stationary phase. It's called PDMS, polydimethyl siloxane. And you make it in the same way that if you've ever played with epoxy, you essentially just pour two things together. You have this kind of liquidy stuff. You pour the curing agent in, and then you're going to stir it up really well. They're being careful about their masses here to make sure they get good molar ratios. You're going to stir it up really well. They're going to go through a bubble removal step, which we're going to skip. And then it's still pourable at this point. So they're not going to do this in a GC column when it's mixed and it's still pourable. This is when they're actually going to expose it to the capillary. So this is showing you making PDMS just a flat kind of rubbery piece. Okay, so it's pourable at this point, and now you bake it. Now, if you have this kind of liquid polymer, this liquid plastic on the inside of a column, it's really easy to bake it in an oven. Now, when you bake this stuff, once you pull it off here, you'll see it's kind of a nice rubbery plastic compound. And that is PDMS, polydimethyl siloxane. I know, again, with the silica, this also originates from silica. But again, silica is cheap and ubiquitous. If you can make something out of dirt, why not? Dirt's great. So if we look at this PDMS, it's this repeating chain. I'll show you a little bit of that in a second. But what's poking out here is two methyl groups. So what's exposed on the surface of this plastic, this polymer, is methyl groups, which are quite nonpolar. So PDMS is quite the nonpolar stationary phase. So it's going to help to retain nonpolar things. Now, this is not like HPLC where the separation is almost entirely due to polarity. Boiling point is also a really important factor in GC. GC retention is a convolution of boiling point and polarity. So if we look at how this PDMS polymer plays out, up top we have a chain. This is what that PDMS would look like. It's a long chain and it keeps going and going and going. But essentially the surface that the analytes are going to see The surface of that rubber coating stuff that's going to be in a thin layer on the inside of the column is just a bunch of methyl groups. So nonpolar things are going to be retained pretty well. But if you are really small and you love to be a gas, you're not going to be retained that well. We're going to call this 100% methyl is going to be the name of this PDMS column. Ohio Valley was the first company to make this. You may still hear this referred to as the OV1 or the DB1. Some example names, the TG1MS, the RXI1MS. If someone puts -1 in there, even though it's a different company, they're probably still talking about a 100% methyl column. This is very common. Another kind of column you can use would be you make a polymer chain that's almost all methyl groups, but you deliberately dope in every once in a while, actually 5% of the time, you dope in a phenyl group. And this sounds funny for me to say this, but relative to methyl, the phenyl group is a little bit less polar. It also can interact, it can grab a hold of aromatic compounds through that pi-pi stacking mechanism. Now these columns are going to tend to be indicated with a -5. So a generic name for this column would be the DB5, indicating 5% phenyl. So you can see here are some example commercial names from ResTech. Instead of calling theirs the RX1, they're going to call it the RXI5 SIL or the RXI5 MS. Thermo's going to call theirs the TG-5 SIL MS. When you see that -5, they are indicating to you the chemistry of the column. They are indicating to you that is a 5% phenyl column, and it has a slightly different interaction. It's ever so slightly less nonpolar than the 100% methyl, the DB1. This is in fact a column that we have in all of our GCs at the moment. And the 100% methyl and the DB5 are going to be the most common sort of go-to generic GC columns. But you can certainly make polar columns. The most common polar column is going to be made from a polymer called PEG, or polyethylene glycol. And all the commercial names that use this column are going to tend to be derivatives of wax. So they're going to call this is the carbo-wax column, or the RXI wax, or something like that. They're going to tend to call these wax columns, and these can have some retention for polar compounds. But again, GC is funny because retention is not just based on polarity, it's also based on boiling point. So you can't use log P or something to accurately predict where something is going to elute, because it's a convolution of boiling point and polarity. And really low boiling point things can be tough to retain in GC. It's only been recently that reliable commercial capillary columns have been developed that will work for blood alcohol, because separating ethanol from methanol from acetone is tricky. They all like to be gases. They're all quite volatile. And so they just tend to blow through columns and come out with a solvent peak at TM. But if you make a polar column with a thick inside stationary phase, then you can get good retention between those different compounds. So in fact, now blood alcohol is also primarily done with capillary columns. Previously, it had to be done with kind of these strange packed GC columns, which is now a pretty unusual arrangement in forensic science. There's probably some of them still around, but almost everything is capillary columns these days in forensic science. So let's check out a cool little video here from Thermo when we consider the effect that having a capillary column is going to have on our chromatography. In HPLC, we said we have almost entirely packed columns. So they've got these guys going through the column, equilibrating, interacting with the coating, the stationary phase coating. They've had to exaggerate the thickness. But let's think about this. There is no packing. So the A term is gone. The A term is gone. There's no multiple paths. Everybody's going the same way. But you have to keep the inner diameter really small for the C term. You have to make sure that those things can reach the wall and have a chance to equilibrate, or the C term will get you. Now, one really big advantage here is going to be there's no pressure issues. There's no packing in your way to mean, oh, if I want to make a long, that's why we can make 30-meter long GC columns, but you're not going to see a 30-meter long HPLC column because you can't get enough pressure. You can't get a pump to push everything through there. But on a GC column, we have these compressed gases, and we can push with a good amount of pressure, but we don't even need that much pressure because it's just an open tube. But you have to keep it small so that at any point in time, the analytes can reach one of the two walls and equilibrate. If you don't keep them small, then the C term is really going to get you. and it's going to ruin your column efficiency and mess up your chromatography. So capillary columns have to have really small inner diameters. Okay, so we talked about columns. Let's look at some components of the instrument now, get into some nitty-gritty engineering things, and talk about injectors, then the inlet, and that'll lead us into a conversation about split ratios. Okay, so we saw this before. We have this inlet where our sample is injected. You can do it manual injection. You can just push it in by hand with a syringe. Most of the time we're going to have the robot, the autosampler, do it for us. And what needs to happen in the inlet is we go from solvent and sample in the liquid phase to the gas phase. And then an appropriate amount of stuff gets pushed onto the column. Okay, so if we take a look at this top here a little bit closer, this retaining ring here is really just to help align the autosampler. It doesn't mean anything as any part of the instrument. So if we take that guy off, we can get a little bit better look at the inlet. The inlet here, you can see it has that narrow focus to help guide the robot. It's very, very hot. It's really hot. Not that I've ever done this before. I have. But if you reach and grab it, it'll burn you and give you a little scar on your thumb for a while. There's the detector next to it. But the inlet's really hot so that it converts our sample into the gas to get it ready to go onto the column. Okay, so injection in GC is really simple. It's much simpler than in HPLC when we had to learn about the valve. We just have the robot go over to the sample, punch through the septum on the top of the sample vial, and then it'll usually sort of rinse this out. Now it's going to swing over, and it's going to make a real quick, sharp injection. It's going to make a fast injection into the GC, boom, and that's the go signal. And now the instrument has started running. So it sprayed this liquid. Now it's going to clean itself a few times, but it sprayed this liquid into the inlet. That liquid's going to explode into the gas phase because it's really, really hot. But what happens in that inlet is really important in GC. Okay, we don't have to worry about a valve like we did in HPLC. That learning about valves and that injection is really annoying. You don't have to learn about that in GC, but you do have to learn about the inlet because the inlet is going to have an effect on the chromatography. Now, in the inlet, you're going to have a liner. It's just a glass tube, a quartz tube, actually, fancy glass, that the sample is exposed to. In this area right here, you have this liner. Okay, so we've watched this video here. This is ResTech showing us, you can see they're putting in the liner. And then on top of that, they have this septum. They have this septum right here. The inlet serves to just be an inert vessel to help transport the sample through the inlet. So it just is something inside the inlet. It's heated, but it's not going to contaminate your sample as it passes through. You have to have the septum there because it's really important that the GC be a sealed system. You don't want any leaks. You don't want outside air. You don't want other gases getting in. So just like you have those septa on the autosampler vial, we have a big thick septum on the top of the instrument. The syringe punches through the septum on your sample to pull up the liquid, and then it goes through to the GC injector port and punches through the septum in the injector port and sprays the sample into the liner such that no gas gets through. Okay, now let's take a close look at what is happening inside that inlet. So we're going to have our carrier gas, the mobile phase, floating through the inlet here. And 1 ml a minute is going to be a really common mobile phase flow rate. But you can see here 104 mils a minute of carrier gas of mobile phase is flowing into the instrument. And you think, well, that's really strange. There's a mil a minute of it getting on the column. 3 mils a minute is going along the top there. That is actually surfaces as a gas barrier to keep any air that might leak in from when you punch the septa coming through. But most of the gas, 100 mils a minute, just blows out into the room. So 1 mil a minute of this gas gets on the column and is actually, that's our mobile phase flow rate, 1 mil a minute. You can certainly do 2 mils a minute, 1.5 mils a minute. 1 mil a minute is really common. But when you do this type of injection, which is the most common type of injection in forensic chemistry, it's called a split ratio or a split injection. When you do this kind of injection, most of the gas that you put in does not get onto the column to act as mobile phase. Most of the gas just gets blown out into the room. So you can see here that we're putting in 104 mils a minute of gas. 3 mils a minute of that is going towards keeping that seal, acting as a helium, if we're using helium carrier gas, or acting as a carrier gas barrier to keep the air out, to help the septum keep the air out. 1 mil a minute is going into the column, and 100 mils a minute is just blowing out into the room. And you might say, why would we do this? Well, let's take a look at what happens when sample is injected. And this is a really excellent animation. This is a really good video. If you're confused about split and splitless injections, I encourage you to go back later and find this ResTech YouTube video at this address that I've shown here. It's probably the best explanation and graphic for splitless injections that I've found. So the ratio of the gas blowing out into the room, that's 100 mils a minute, to the ratio of going on the column is called the split ratio. In this case, we have 100 mils going out, 1 mil going into the column, so we would say it's 100 to 1 split ratio. 5 to 1 to 501 are common. So here comes the sample, it's injected, goes on the glass wall, it's vaporized, turns into gas. Now most of that gas blows out into the room and a little plug gets on the column, but most of our sample just blew out into the room. And this is going to seem a little counterintuitive at first because you think, why are we getting rid of all that good sample? Why are we just wasting all that signal? So first, let's consider what this split means. Let's suppose we have a 1 milligram per milliliter solution that we're going to inject into the GC. Now, a really common amount to inject would be 1 microliter. So if we're injecting 1 microliter of a 1 milligram per milliliter solution, if you do the math, you'll find that we are injecting 1 microgram of sample into the liner. Now let's take a look at that table we were looking at earlier from Sigma Aldrich. Okay, so if we have a 0.25 millimeter inner diameter column, which is really common, the capacity of that column is 50 to 100 nanograms, or 0.05 to 0.1 nanograms. That's well below the, 0.05 to 0.1 micrograms. Yeah, that's well below the 1 microgram that we've injected into the column. So we are overloading the column. We're overloading the column if we inject 1 microliter of 1 mg per mil. And it's really annoying to have to keep diluting our sample, but if we don't, if we inject too much stuff, these capillary columns, they can't handle it, and we're going to have overloading, and we're going to get peak fronting and poor peak shapes. So this is actually helping us. Most of the time in GC, you actually need to dilute your sample on the way in. So you set your split ratio, that's a quick dilution that's done for you in the instrument. So when we set a split ratio of 100 to 1, it's diluting our sample by 100 times for us. It's diluting it from 1,000 nanograms or 1 microgram going onto the column to 10 nanograms going into the column. Now, if that didn't give us enough signal, we could just go in the software and change the split ratio to 10 to 1 or 5 to 1. But it's a really nice, simple feature that lets you control how much is getting on the capillary column so you avoid overloading it, but you make sure that you get enough signal. Now, in forensic drug chemistry and seized drugs and seized explosives and things like that, we tend to have tons of material, so we're almost always going to use a split. But GCMS and GC are quite useful in toxicology, and in toxicology, you're really pushing for everything you can get. So in that case, you actually are going to turn the split off for what's called a splitless injection. So the split will be operating normally, but then you tell the instrument when you're about to inject, turn the gas flows nice and low. So you still have that septum purge, as they call it, the thing to keep the air out, but now you're just putting the 4 mils a minute, and the gas you're putting in goes in the column. Okay, so you inject your sample, it becomes a gas, and everything in the inlet is getting pushed into the column. So the split is off. But then the truth is, after just a couple seconds, you turn the split back on because it's too much. The time that you have the split turn off for is called the splitless hold time. So the splitless can let you push a lot more onto the column. So if you're operating at really low concentrations, then a splitless injection is a good option. In toxicology, if you're dealing with really small amounts of stuff, you can do a splitless injection and still not overload the column. So splitless is going to increase your sensitivity, but here's a really nice example where they looked at some components on the surface of green peppers, and you can see they had a good amount of material, And with their splitless injection, you see that they got pretty severe peak asymmetry. Their peaks are misshapen, and their chromatography is not great for those first two peaks. So when you can do a split injection, it's going to help your peak shapes come out nicer, and it's going to get you where you need to be in terms of getting the right amount of sample onto that little capillary column and making sure that you don't overload it. When you have to, because you're really pushing sensitivity, then you can switch to a splitless injection. So when we talk about the inlet in GC, we need to talk about a really important aspect of GC, and that is we are forming gases by heating liquids. So if you want to analyze with something with GC, it has to be a liquid that when you heat it, or has to be a sample that when you heat it, it converts to a gas intact. And it's not uncommon for things to degrade. We call this thermal degradation. So some things don't like being heated and they fall apart. They react in the heat. It's also true that a lot of things, bigger molecules, just don't evaporate when you heat them. You can't take proteins and heat them and evaporate. If you're cooking eggs, egg whites are almost entirely protein. And when you drop egg whites in a hot frying pan, they don't vanish and evaporate. You can't take proteins, heat them up, and have them go in the gas phase. You just get cooked eggs. And actually in GC, what will happen is if you take something like that and you try and inject it in, then your liner will just be covered with goop because you've just baked things on the inside of the liner. So a number that you'll commonly hear, I've seen thrown around in several books, is only 20% of compounds are amenable to GC because they have to be okay with being heated in the inlet and converted into the gas phase just through heating. Now that being said, almost all forensic analytes do really well with GC. GC is an amazing technique. You get those long columns. It's really hard to beat the efficiency and the chromatography of GC. But you do have to keep in mind that there are some analytes that do not like being heated. And that's why it can be really nice to have an LC around also, because LC is going to be much gentler on analytes. It's not heating them. So what I'm showing you here is a classic example of thermal degradation in forensic chemistry. This is psilocin and psilocybin. And as you can see, psilocybin has that phosphate group. And when you heat it, it falls off and leaves you with psilocin. So if you have pure psilocybin and you heat it, you can wind up with entirely psilocin. And then as a matter of fact, psilocin can actually thermally degrade itself, but you don't typically see that in the time course of a GC run. But what is true is if you have a magic mushroom sample that has both psilocin and psilocybin in it, you have to be very careful how you call that case, because it's possible that you have mostly psilocybin in that mushroom. You inject it into the GC port, and in the GC injection port, the heat in there converts the psilocybin to psilocin, and you only get a peak for psilocin. And you never saw the psilocybin that was in there. Or it could be that the mushroom has mostly psilocin, and you inject the extract into the GC port, and you get a peak for psilocin. So that is to say, you're going to get a peak for psilocin very likely, whether or not it was in there in the first place. If you had psilocybin in there, you're going to get a peak for psilocin. If you had psilocin in there, you're going to get a peak for psilocin. Sometimes you get a little bit of a psilocybin peak, but mostly you're going to get psilocin. So if you go to court and you just look at your GC or GCMS data and you say, I had psilocin, I'm reporting psilocin, you need to be careful in there, because if someone asks you, could that have been psilocybin that interconverted to psilocin, you say, yeah, that's certainly possible. That could have happened. The thing is, they're both controlled, so it's not as important here. But this is a classic example where if we have a sample that's a mixture of psilocybin and psilocin and we run it on GC, we really can't be certain of how much psilocybin or psilocin we started with, because most of it is going to convert to psilocin in the injection port. You can also get thermal degradation as the sample travels through the hot column, but that is less common than thermal degradation in the inlet. Split injections cause less thermal degradation than splitless injections. Splitless injections are going to result in more thermal degradation. Now, this is not very common. It's not very common, but it's something that you should be aware of. So let's look at some examples of this and some ways that we could ameliorate this. Okay, so here we have a synthetic cannabinoid, 5-fluoro-NPB22. You can see that guy up top. And when you run it in methanol, you get a good amount of degradation there into the quinolone, that peak C. And when you run it in acetonitrile, it turns out this is actually facilitated by, it's called hydrolytic cleavage. But in acetonitrile, the thermal degradation pathway is a little bit different, and you actually get this imidazole methyl ester analog. So to say here we have this synthetic cannabinoid where we're going to get one peak for the cannabinoid, but we get a peak in that spectrum, or we get a peak in that chromatogram, that peak C, both in methanol and acetonitrile, which probably were not in the sample in the first place. They were just generated in the inlet through thermal degradation. One way that you can deal with this that we don't use real often in forensic drug chemistry because it's just not worth it, it's a lot of work, it's called derivatization. So here you see, these are actually mass spectra, but there's this 25C N-bomb compound on the bottom, which can sometimes undergo thermal degradation. On top, you see the what's called trifluoroacetic derivative, the TFA derivative. So see that amine group there is derivatized, we would say on top. This is that annoying protecting group stuff that you did in organic. So we can actually make our drug undergo an organic reaction that we know about so that it will be protected from thermal degradation. This can also be used to make things that don't evaporate easier. Some derivatives help things evaporate. Now these derivatization kits that we don't have to do fancy organic, it's not a big organic reaction, they're usually sold as kits. And the two common reactions are going to be trifluoroacetylation. This reacts with amines. So you take this amine and you take this trifluoroacetic anhydride on top. Now you have to mix it in water-free conditions. This is actually very similar to the aspirin synthesis that you did in General Chemistry 2 lab. Silylation is common for hydroxy groups or phenol groups where you put a trimethylsilane on the compound. This helps to make things more volatile, and it also protects those alcohols that can cause problems with chromatography. This also ends your tailing that you see with amines. So derivatization sounds great on paper, but it's a lot of work, and most of the time we just skip it and seize drugs. Okay, so we've gotten through columns, injectors, inlets, and split ratios. Now let's talk a little about the mobile phase. Let's talk about carrier gases. And then we'll talk about the oven and temperature programming, which is going to be a big part of controlling our chromatography and improving our resolution and such. So let's revisit our old friend Van Deemter. We have a Van Deemter plot here, which you'll recall is plate height on the y-axis versus flow rate for the mobile phase on the x-axis. So we are not going to change mobile phases in GC. Do not, on an exam, say for HPLC, oh, you know how I'm going to fix this? I'm going to run a temperature gradient. No, you're talking about GC. Also, do not say, if you're talking about a GC run, don't say, you know what? I'm going to change the mobile phase composition. I'm going to change the percent of this or the percent of that. There's no acetonitrile or methanol or solvents here. These are gases. And we're really only going to pick one of three gases, pretty much, and we are going to stick to it. There are some exceptions. There have been several GCs that have gone to space, gone to Mars and things, and they'll use the Mars atmosphere, which is mostly CO2 for carrier gas. And then there have been some instances of portable GCs where they've used air for carrier gas. But for the most part, in the lab, you're going to see nitrogen, helium, or hydrogen. Now, nitrogen is cheap, and air is 78% nitrogen. But as you can see, you can't go fast with it. If you go fast with it, the C term is terrible, and it's going to punish you, and your chromatography is going to be terrible. So it's pretty rare to find someone in a forensics lab that's using nitrogen. In the United States, it used to be everybody did helium, and we are still using helium because in the United States, we do a lot of natural gas mining, and helium is a byproduct of that industry, so we have plenty of helium. But helium is a completely non-renewable resource. So those fun little helium balloons you have, when the helium is released from there, it is not contained by our atmosphere. So that helium shoots into the sky, through the atmosphere, and into deep space, and is gone forever. So the cost of helium over my career has increased enormously. Enormously. We used to pay something like $20, $30 for a tank of helium. And those tanks of helium you see next to the instrument now are $800 at the moment. So when you watch that PSI ticking down, just think, oh my gosh, that was $800 that just blew out into the room and through atmosphere and into deep space. So helium's a really good carrier gas. Hydrogen, if you look at it, you think, oh, hydrogen is the best carrier gas. Why don't people use hydrogen? Well, until pretty recently, there's a good reason that people didn't use hydrogen. Why would we be hesitant to use hydrogen gas? I would encourage you to think about the Hindenburg. Yeah, that's right. If you have a big tank of hydrogen gas and you're putting it in an oven, then you really have to worry about things exploding. So it used to be when you used hydrogen, you had to purchase an explosion-proof oven. And it doesn't mean that if your oven did explode, oh, everything's fine, we go back to the instrument. It just means it wouldn't kill you. Your instrument was destroyed, but it was okay. But there's been some recent developments in what's called hydrogen generators that have made hydrogen much more appealing. And in the long term, it's much cheaper to purchase a hydrogen generator than it is to continue to purchase helium gas. We use helium for right now at UT, and you're still going to run across a lot of crime labs that use helium. But it's an interesting time in the United States where there's a big push to transition from helium to hydrogen because of the cost. But you're going to pick one gas. This is going to be your mobile phase. We call it the carrier gas. You're going to pick one gas, and that is your mobile phase. You don't do mobile phase gradients. You don't say, oh, I'm going to start off with 10% helium, 95% hydrogen. No, you have one tank of gas or one generator, and that is what pushes through your inlet and pushes the stuff onto the column. That is your carrier gas, and it's a very big deal to change it out. So I mentioned hydrogen generators earlier. I want you to be aware of those because more and more you're going to see labs have these things. They're quite cool. So if you have water and you run current through it, then you electrolyze the water. You convert it to those bubbles are hydrogen and oxygen gas. So you can just split the water into hydrogen and you can purify it and get really pure gas for GC. So you can just have this little hydrogen generator sitting there next to your GC generating hydrogen gas for you. And the reason this makes everything quite safe as opposed to a big tank of hydrogen gas is if you have a big tank of hydrogen gas and you're pushing it through your GC, if there's a leak somewhere, particularly in the oven is just going to fill with hydrogen gas. The tank's just going to keep pushing hydrogen gas in there. The oven's going to fill with hydrogen gas, and you've got a flame detector there. Eventually, it's going to explode, and it's going to essentially act as a bomb, and that can be quite dangerous. So for a long time, people were very concerned, understandably, about the safety of using hydrogen gas. With a hydrogen generator, though, you put that water in there. It uses the electrodes to generate the hydrogen. It purifies it, and it just makes little bits at a time. It makes hydrogen as needed. So there's not this giant amount of hydrogen that can pool up. The other thing is there's a bunch of leak sensors, and if it ever detects, oh, I'm putting out a bunch of hydrogen, there's a leak, then it just stops. So these hydrogen generators are quite safe. They're becoming more and more popular. I know our medical examiner's office, the toxicologist there, switched over to hydrogen a couple years ago, and this is definitely kind of a thing right now, where when you go into crime labs, you can look at their instruments and see if they have these boxes, these generator tanks in their instrument, or if they still have big tanks like we do. Either one is fine, but it turns out that hydrogen is becoming cheaper than helium and is quite the reasonable alternative when you use a hydrogen generator. Now, we have this oven, and we can change the temperature as we do the run, or we can keep the temperature constant throughout the run. If we keep the temperature constant throughout the run, we call that isothermal. And this is going to be the easiest thing to change your chromatography. It's just punching some buttons in the software. Much easier than changing a column, certainly easier than changing your mobile phase, your carrier gas. Changing the temperature is your first go-to to improve your chromatography. So what we can see here is, this is from your Skoog book. You can see that if we run an isothermal at a lower temperature, then the peaks that elute later, there are supposed to be 9 peaks here, take a really long time to come out. They take a really long time to come out. But if you raise the temperature of that isothermal, so they go from 45 to 145, then it pushes the late eluting compounds closer to TM, pushes them, makes the runs shorter, but then the peaks, 1, 2, 3, 4 that were already close to TM, they get pushed into TM and they're gone. They're not resolved. Now, if you just have one or two compounds and they both have pretty similar elution times, use isothermal. When you can get away with it, use isothermal. It's faster and easier. But if you have some compounds that elute quickly on the column and some they're low boiling point or they're non-polar, or they're polar or both, they're polar and they have low boiling points. And then you have other things that are huge, high boiling points and they're non-polar and they come out real late, you're going to have to run a temperature program. So that's what they've shown in this third picture here, where they start off at a low temperature, and that allows efficient separation of those polar or low boiling point compounds. And then they raise the temperature in a consistent ramp as the run goes on, and that allows these later eluting compounds to come out. So if you have a range of polarities or boiling points, you really need to run a temperature program. If you don't, do isothermal. If you can get away with it, do isothermal. This is exactly analogous. The skills you do here when you practice this is exactly analogous to running isocratic versus a mobile phase gradient in HPLC. But do not confuse them. Do not say on an HPLC, oh, I'm going to run a temperature gradient. And do not say on a GC, you know what, I'm going to run a mobile phase gradient. I'm going to shoot acetonitrile and methanol through the GC. No. That doesn't work that way. So let's take a look at another couple examples. Here's just a straight up alkane, and this is a wide range. You've got from C6 to C21 here, so this is a wide range of eluting compounds. You're not going to get away with an isothermal. You need to run a temperature program, and you can see their temperature program at the bottom where they go from 50 to 250 at 8 degrees C per minute works out great. But also, let's take a look at the influence of running a ramp. So we can get a feel not just for, oh, this should be isothermal or this should run a ramp. We also want to get a feel for how could I change a ramp to improve my chromatography. So we look at the isothermal, you can see it's too hot for the little guys. And if you're too hot, or in the case of HPLC, if you have too much %B, you push things into you push things into TM. I should say, you push things into TM, you squish things up front, and they're unresolved. But if you have things that there's way too much space, so if you look at C13, C14, C15, that is a waste of time. You do not need all that space between those peaks. So you look at this and you're saying, you look at the front and you're like, I need to be cooler. I need more time because I need to spread those out. You look at the back end and you say, I need to be hotter because I need to push those peaks together. I need to push those peaks closer together because I'm wasting time, having so much time between them. So kind of the ultimate in separation you can get is just if you're running isothermal. So here, let's look at an example of this, where they've got a bunch of different peaks. They start off at 100 and they go isothermal because they want those 3 peaks to make sure they elute. And those 2 guys right there, right around 15, 16 minutes, they're really close to each other. So they're playing it careful and doing an isothermal there. They're doing an isothermal there to make sure that they get those 2 guys resolved or as close to it as possible. But look, as soon as those guys are resolved, they crank up the temperature again. They crank up the temperature again and run a ramp up to 160 degrees. And they're going to hold it 160 degrees because they're also worried about those peaks right around 36 minutes. If you look at those guys are barely resolved. They want to go nice and isothermal. They can run nice and flat there because the more you ramp, the more it pushes things together. But when you don't ramp and you just do isothermal, you can be wasting time and things take forever to come out. So they hold at 160 to resolve as best as possible those peaks around 36. Now, in truth, if they wanted to fix this, they might ramp to a lower temperature. They might ramp to 150 or 140 and hold there and see if that would help spread out those peaks that are right now around 36 minutes. But they get those peaks resolved and then they ramp again up to 220. And they do a pretty good job of resolving those peaks there. But you could say they could play a little bit more with their ramps, maybe make their ramps a little bit more gentle, maybe make some of their temperatures lower. They're already at 60 minutes. So at that point, it gets pretty tricky. And maybe they just said, well, we can see all these different peaks. We're not going to worry about them being completely resolved. You really have to go into the lab and do this. There are some good simulators out there, both for HPLC and GC. But this idea of ramps and flat, this is common to both GC and HPLC. But in GC, it's temperature. In HPLC, it is solvent. We've talked about columns, stationary phases, and we talked about the injector, the inlet split ratios, and then we talked about the mobile phase, the carrier gas. And we also talked about column ovens. Let us finish up with a discussion of detectors and look at some example data. Okay, so I'm going to dredge up some painful memories here from Gen Chem of electrodeposition or electrochemistry, because we have to talk about ions and voltage and current. So here we have an anode and cathode, we have brass and copper, and if we're using a battery to apply a voltage to the cathode, the positive ions move towards the negative cathode and deposit on the cathode. When they do that, current flows. Now, current is good signal. It's really easy for us with electrometers and to read current and voltage. So whatever detector we do is ultimately going to get converted to current or voltage. Okay, so you did this with electrodeposition when you did electrochemistry. But now we're going to do that with, it's mostly going to be gases and things. It's not going to be often that we put cathodes and anodes into solution when we're talking about detectors. Think about how detectors fundamentally detect. It's really common for us to have some photons or some ions or some chemistry, and we want to detect something that's going on there, and ultimately the signal will usually be current, voltage, or frequency. So current comes up a lot because if we create a charge gradient, we just sort of have charged plates or something that we're applying voltage to. In the previous example, like you guys did in electrochemistry, it was a battery. It can be a power supply or a battery or anything that you can sort of plug in and apply voltage with. It could be a phone charger. A phone charger applies 5 volts and then provides current. Current runs from the phone charger to your phone and charges the batteries. That's actually an electrochemical reaction where you are pushing electrons into the phone to reverse the battery reaction so that when you unplug it, the reaction will go in the forward direction and supply current to the device without having to be plugged in. This is not uncommon to apply voltage to something such that we have a positively charged plate and a negatively charged plate, or an anode and a cathode. And if we somehow generate ions, if we have a neutral compound and we convert that into ions and electrons, if we have ions and electrons in here, the electrons are going to be attracted to and deposit on the positive plate. The ions are going to be, the positive ions are going to be attracted to the negative plate and deposit on the negative plate. And when these things deposit, then current flows. So if we generate ions and then we have a positive plate and a negative plate, the positive ions will deposit on the negative plate, the negative ions or electrons will deposit on the positive plate, and when they deposit, they generate electricity. This is exactly like the electrodeposition that you previously did in electrochemistry. We measure the current that results from this, and the current is directly proportional to the number of ions that impacted the plate, or the number of electrons. This theme of, whatever signal we have, whatever we're measuring, if we're measuring light, or we're actually measuring ions, or we're measuring whatever, we're going to convert them to electrons or ions, usually electrons in the end, and then let them impact something and measure the current that results. Or you can also just separate positive and negative charge, and the separation of the charge will yield a voltage that you can measure. With that discussion out of the way, let's look at our first GC detector, the FID, or flame ionization detector. You need hydrogen, air, and nitrogen gas, and then you need electrical connection to the cathode and the anode. So what we're going to have here is we're just going to make a flame. We're going to make a flame with hydrogen and the oxygen in the air. You're going to have a flame jet. We're going to use this makeup gas it's going to help sharpen up our peaks. But for the most part, you essentially are just burning your sample. The capillary column comes up and it gets burned up in the flame. Now, the trick is with FID, the flame ionization detector, is it's sensitive to carbon. Carbonaceous compounds, organic compounds, burn up. They burn up in this flame. They get reduced to methane, and then methane undergoes this reaction in the hot flame where it tends to yield the formylium ion. So when you have these big organic compounds and they get burned down to methane at the base of the flame, and then later in the flame, that methane gets converted to formylium ions and excess electrons. So now we have ions and electrons, and now that we've ionized something with the flame, we've flame ionized something, now we can detect it with current. So here's a little bit more in detail schematic. We have a collector at minus 200 volts, and you can see the torch itself is at ground or 0 volts. So the positive formylium ions are going to be attracted to the collector, and they're going to collide with the collector and deposit, and that's going to generate a current. So we can just read the current, and that current is going to be proportional to the amount of carbon that was in the flame. So the FID detects carbon-based compounds. It detects organic compounds, carbon-based compounds, and the detector response is proportional to the amount of carbon. It's a very powerful, ubiquitous detector. A second detector that is much less common than the FID, but important in explosives detection, is the ECD, electron capture detector. This is going to rely on an anode composed of radioactive nickel-63, and then the cathode, which detects the current coming from the nickel-63. Again, that's radioactive. Okay, nickel-63 is a beta emitter, and so I'll dredge up those memories of it from general chemistry when you did radiochemistry. Nickel-63 is a beta emitter, but remember, beta particles are just electrons. They're electrons. They usually have a decent amount of energy, but they're just electrons. So if I have a film of nickel-63, it just sits here spontaneously and shoots electrons. It just sits there and emits electrons. So if we put a plate here that has positive charge on it, these guys are going to deposit at the positive plate, and that is going to result in current, a flow of current. So just by putting nickel-63 in front of a positively charged plate, you're going to read a constant current. Now, the trick with the electron capture detector is that if we put our GC capillary right here, and we have something that flows out, so the most famous ones would be halogens. So I'll just say some chlorinated compound. Okay, if that enters into here, it turns out that halogens can absorb electrons, or we say they capture electrons. They undergo a reaction where they capture electrons and hold on to them. So what's happened now is that electron is gone. It doesn't impact the positive plate because it was essentially absorbed by, it was captured by the halogenated compound. So it is gone. That electron is gone, which means there is less current. So the trick here is, if we look at the electron capture detector and we measure the current versus time, there's going to be some steady state electron current, some steady state current due to the electrons. But when something comes out of the column that can capture electrons, some of those electrons are going to go missing. They're not going to hit the plate, and the current is going to dip. So we just take this and flip it over, and that's our GC peak. Now, in truth, this is a bit simplistic. It presents the basic, the physics of the idea, but in truth, what they actually do is they apply voltage pulses. They apply pulses at a specific frequency to maintain the current. And when the current drops, they have to apply more pulses, and they read that out. We don't need to worry about that. You'll be okay if you understand that compounds that are capable of capturing electrons will take electrons away and cause a dip in the current that we read from the detector. So one great thing about the FID is it's sensitive to and detects all carbon-based compounds pretty easily, but the ECD has a wonderful niche because it ignores most compounds or is very insensitive to them. It's extremely sensitive to halogens, pretty sensitive to nitro groups, and a couple others. And this can be pretty powerful because when you're detecting explosives, it will ignore a lot. If you have a really messy mixture, it'll ignore a lot of the junk in the mixture, but it'll pick out the explosives really, really sensitively. So here we have the same run that was done with an FID and an ECD, and it's a complicated mixture. Look at all those peaks. Now they've sort of tilted the chromatograms on their side here, but you can see with the FID, tons and tons of peaks. But on the ECD, it ignores most of the compounds because most of those compounds don't have halogens, fluorine, chlorine, or nitro groups, or nitriles or organometallics. So all you're going to see on the ECD detector with great, exquisite sensitivity is going to be nitro groups, halogens, it's exquisitely sensitive for halogens, and a couple other groups. So the ECD can be a really nice niche detector when you want very sensitive detection, or if you have a messy matrix and you just want to pick out those halogens or nitro groups. All right, now a really, really, really important detector in gas chromatography is the mass spectrometer. There are a lot of different types of mass spectrometers. We will get into that in a big way in the next videos and next bit in class. But this type of mass spectrometer is going to be a little bit different than when we hooked up to the LC for LCMS. And we'll talk about that a little bit in this video. But the idea of the three-dimensional data is the same. You're actually getting a full mass spectrum. You're getting full category A data for every point in that chromatogram. So we can scan through all the different spectra and get all kinds of information. This is very analogous to what we did in LCMS in the previous video. We are not going to get into the specifics of the mass spectrometer here. We're going to leave that for the mass spectrometry section. But let's take a look at some of the data. So let's zoom in on one of these peaks. Okay, now this is the mass spectrum for this peak, and you can see that there's these discrete points. There's one spectrum, and then the next spectrum, and the next spectrum, and the next spectrum. So we have 4 or 5, looks like maybe 6 mass spectra across the peaks. Let's look at the mass spectrum at the peak here. Now there's not just one peak that represents the protonated molecule like we saw with LCMS. There's a bunch of peaks. This is what we call a fragmentation spectrum. So the ion sources for mass spectrometry that are usually used with LCMS give ions that are typically the protonated or deprotonated molecule. So they represent the intact molecule. The most common ion source there is going to be called electrospray ionization. That's the most common ion source in LCMS. The most common mass spectrometer ion source for GCMS is called electron ionization. And this is a higher energy ionization, and it fragments the molecules. So you get a bunch of peaks at a bunch of different masses, and this represents the molecule broken into pieces. Now the beauty of this is this fragmentation pattern is pretty reproducible. So this is really powerful category A data. This is information-rich data. It's going to be similar to IR in that it's a category A technique, and you're going to be able to pick out what this is pretty easily most of the time with a library. So this guy has a built-in library search here. And library searches are powerful tools to point you towards what standard to pick. But remember, you always make comparisons ultimately with positive controls or standards. So nonane. So this was an alkane. This was a series of alkanes that we're looking at. And that peak is in fact non-A. We can compare it here. We can look up other information. Again, you use library spectra to use library searches to point you to the right standard, but you always base your analysis off comparison with a positive control, a standard. Here we have a GCMS chromatogram up top of 3 drugs, 2 of which are scopolamine and cocaine. This is the famous mass spectrum of cocaine, the 82, 182, 303. So we did a search, and it's going to pull up that is likely the mass spectrum for cocaine. We could go get a cocaine standard and run it and find that it is in fact cocaine. Now, cocaine has a mass of 303, has an molecular mass of 303 Daltons. So we don't get a protonated molecule at 304. We get an actual, we call a molecular ion at 303. But we also get the main peak in the spectra are fragments. These fragments are 82 and 182. Now, if you look at scopolamine, it's quite a different mass spectrum, but it still has that 303 because, in fact, so we'll search this guy and find that it is scopolamine. Scopolamine and cocaine are isomers of each other. They both have a molecular mass of 303. So they both give that 303 peak, but they give different fragments in the fragmentation spectrum. So we can tell the difference in the fragmentation spectrum. But in LCMS with an ESI source, they would both give us the proteinated molecule at 304. Now, because we have this three-dimensional data, this is going back to our alkane mixture. Because we have this three-dimensional data like we did with LCMS, we can look at chromatograms that are either the TIC, the total ion chromatogram, or we can look at chromatograms that are a function of specific ions present in the mass spectrum. So if we poke around in this mix, we see that, there we go, on decane, we can pick out all these things that were in the alkane mixture without having to count here and count there. But look at this, we have 43 and 57 for that alkane, 43 and 57 for the previous alkane. I went all the way out to let's go all the way to C36 here, 43 and 57. It turns out that compounds that have similar structures a lot of times give similar ions in their fragmentation spectra. So I'll search this guy here and we'll see that this is C36. So we looked at, I think C10, C12, and now we're at C36. And their mass spectra all have this 43, 57, and 71. And it turns out that that's common to alkanes. It's very common for alkanes to yield 43, 57, and 71 fragments. So we can take advantage of this by, here's another alkane with 43, 57, 71. So we can actually tell, just like we did with LCMS, where we say, you know what, instead of doing the total line chromatogram, show me a chromatogram for a specific mass. So if we say, show me the signal for a chromatogram for just the 57 peak. So based on now, the fact that those two match up, that we already know this is an alkane mixture, but the fact that those two match up tells us that, well, all of these things, all of these peaks have the 57 fragment in them. It turns out that 57 is pretty indicative of alkanes. So we can start to look at classes of compounds by doing these selected chromatograms. These are often called selected ion profiles, and they're going to be very important in fire debris, because recall in fire debris, it's going to be a very complex mixture of compounds, and we're most interested in what classes of compounds are we looking at here. Are we looking at a bunch of alkanes? Are we looking at aromatic content? And there are going to be ions. So here I picked one specific ion that was specific for one of the alkanes up top. But you can see if we pick ions that are common to all the alkanes, then we can pick out, this series of peaks, these are probably all alkanes. That's going to be very, very useful to us in looking at ignitable liquids. Let's look at a specific example. This is a chromatogram for an ignitable liquid. It's kind of complicated. It's actually not too bad for an ignitable liquid. But if we want to start asking ourselves something like, okay, we'll poke around here, look at some of the mass spectra, but then we say, what's the alkane content? What's the alkane content of this ignitable liquid like? That's going to tell us a lot about what it could be. So what we're going to do is we're going to say, show us these mass ion profiles for these ions that are indicative of alkanes. So 57 is a good one, 71, and we're going to type in a few of these ions. Okay, and we can see, oh look, there's all these different ions, and each of those peaks has those ions in it. A better way to do this is to actually go through, let's get rid of these, and to say, show me the sum of those ions. Okay, so let's do that now. We'll say 57 plus 71, and we'll go in and we'll punch in these ions that tend to be indicative of alkanes. And now this is essentially an alkane chromatogram. And we can see that this thing has a lot of alkane content in it, and it turns out this guy is diesel fuel, and it has a lot of alkane like we'd expect. Now we can punch in aromatic content, and we can say, ooh, this thing doesn't have much aromatic content at all based on these mass profiles or these selected ion profiles. So this is the primary tool we're going to use to characterize ignitable liquids. We are going to run GCMS, and then we're going to break them down into selected ion profiles for alkane content, for cyclic aliphatic compounds, for aromatic compounds, for all those groups in that ATF sheet. And we're going to say, okay, what's the primary composition? Look at this one. We've only looked at alkanes and aromatics, but we can see, oh, this is mostly alkanes. We can also look at the range. How big are these things? If we compare them to the alkane standard that we ran, we can say, what are the range of these peaks? Does it come out more consistent with the heavier alkanes? Is this a heavier distillate or a heavier fuel? Or does it come out in the middle or closer to the beginning? So we can characterize it in that way, and we can also characterize the basic chemical content. So this guy is in fact a diesel fuel, and we would expect a lot of alkane content from diesel fuel. It's primarily alkane content. So this is what we are going to do for ignitable liquids. Instead of paying attention to mostly specific mass spectra, we're going to pay attention to these selected ion profiles, these chromatograms that are indicative of different classes of organic compounds. There are a lot of different GC detectors. We only covered a few, but I want to cover one more, kind of an up-and-comer, GC-IR. So you can take a GC, this is our thermo-GC, and this actually our thermo-IR, and you can connect them. And this is going to be a little bit analogous to GCMS in that you get different peaks and you get IR spectra for each peak. Now, it's not going to be as sensitive as GCMS, but we'll see why this guy can be quite useful in just a minute. And back in my day, this was sort of a weird esoteric thing, but the technology has really come along, and it's definitely an up-and-comer. The Pinellas County Crime Lab uses these. That's a great crime lab. They're very innovative and kind of stay on the front of things. But you're going to see this a lot more in crime labs, particularly for seized drugs. So let's look a little bit about how this guy works. So you're really just going to bring your GC column into a special cell called a light pipe that you put in your IR, and this is going to be a lot like transmission mode. It's a transmission mode IR, like we saw in the video, except instead of a pellet, you have a gas chamber. You bring in the gas through a heated inlet from the GC, and it passes, so the light pipe is filled with the gas from the GC, and then that gas eluent comes out. It's not destroyed, so if you want, you can actually feed, after it gets detected by the IR, you could feed that gas eluent into an FID or an ECD or even, in theory, a mass spectrometer. You might get a little bit of band broadening from the light pipe, but it doesn't destroy the sample. You could keep going with it. But most of the time, people are just going to do the GC-IR. So you're going to get peaks here from the GC, but for every peak, or really for every point in time, you're going to get a full FTIR spectrum. So let's look at some data here. This is the QC data run by one of our alumni, Abigail Hawk, at the Pinellas County. She works now at the Pinellas County Forensic Laboratory. So we have a mixture of compounds. We have a chromatogram, as you'd expect above. You have to pick how you're going to display the chromatogram. You can just do it as the sum of all the peaks in the IR. But then for every peak you get, or really, again, for every point in time, you're going to get a full IR spectrum. And you can perform library searches on these peaks, And then you can go find standards, and you have a category A analysis. So this is an impure sample. This is a mixture of 5 different things, which would normally give you a low quality IR spectrum as a mixture. But because we've separated them out here and gotten individual spectra for each peak, we have high quality IR spectra. So you can see over there at that 6.44 minutes, that is a cocaine spectrum with the library search underneath it. One thing you might be asking yourself is, why are the peaks poking up instead of poking down? It doesn't matter. When we get to spectroscopy, we'll talk about that. You can plot IR peaks as absorbance, just like you do UV spectra, or transmittance. Transmittance, they hang down. Absorbance, they poke up. It's the same spectra, just 2 ways of plotting it. So this is quite powerful. It's less sensitive than GCMS, so you're not going to see it really employed in toxicology. GCMS is an integral tool in toxicology. But for drug chemistry, when you're trying to tell the difference between closely related compounds, this is a really, really powerful and useful technique. Let's look at some examples as to why this is. So this is a fentanyl derivative that's shown up around Florida, excuse me. And it's fluorofentanyl. You see there's a fluoro group. There's a fluorine on that aromatic group on the end there. And you can see we're looking at 3 mass spectra, 3 fragmentation mass spectra from GCMS. The first is the ortho substituted fluorine, and then we have the meta substituted fluorine in the next one, and then finally the para. Now, mass spectrometry can have a really difficult time distinguishing between ring substituted isomers like this. If you just roughly look at those EI mass spectra, you can sort of see the position on the x-axis of the peaks are the same. The relative intensities are a little bit different. But it can be really difficult to distinguish these reliably, and it can be hard to go into court comfortable saying, oh, this was definitely the meta isomer of, this is metafluorofentanyl as opposed to parafluorofentanyl. That doesn't really matter. They're all controlled, and you can say an isomer of fluorofentanyl, but it sure is nice to know. And it can be a little bit hard based on an GC mass spectrum, the mass spectrum from GCMS alone, to reliably distinguish these guys. Now, they have different retention times. They give different peaks in the chromatogram. You can see the ortho has a retention time of 8.86 minutes, the meta 8.69, and the para is 8.73. And so with reasonable chromatography on GC, those should be distinguished. So you can use retention time if you need to, but it's still a little bit uncomfortable to have that category A data that makes it's difficult to distinguish between those guys. So you can just report it as an isomer of fluorofentanyl, or you can combine this information with GCIR and be certain. So if we look at the IR from the GCIR for these 3 compounds, the ortho meta para, we can see that there are some distinct differences, particularly if we look over in the fingerprint region. We're able to pick apart those differences. There are definite differences there that we can pick apart, but also certainly if we had run as a test our GCMS as one of our tests and GCIR as our other tests, that's going to give us a really high confidence, even in distinguishing between those ring substituted isomers, which is a difficult thing to do. So GCIR as a kind of reliable standard is kind of a new kid on the block. Like I said, they had some variations of it back when I was in the crime lab in 2000, but it was a difficult instrument to use. It was tricky, and it wasn't that reliable. It kind of broke a lot. But they've really come a long way. These are pretty good, reliable instruments, and I think they're going to show up more and more in crime labs as people struggle to distinguish some of these closely related designer drug cathinone and fentanyl and synthetic cannabinoid derivatives that just differ by a ring substitution or some really close substitutions. There's also some issues sometimes in GCMS where you get some ions that really, really like to form, and they make these big peaks that sort of drown out all the other peaks. That's particularly true of phenethylamines and some cathinones. We'll talk about that when we get to GCMS. But GCIR can be a really nice complement and a really powerful technique. And I do also want to thank Rita Newman at the Pinellas County Crime Lab, the forensic laboratory, for sharing this data with us. So, we finished gas chromatography. We talked about columns, the stationary phase. We went over the injector and the inlet. and then that led to a discussion of split ratios. We talked about the mobile phase, which is the carrier gas, and is quite different than the mobile phase in HPLC and liquid chromatography. Then we went over column ovens and temperature programming and talked about FID detectors, ECD detectors, mass spectrometers, and IRs as detectors with accompanying example data.